Next is session 2C, and I invited 7 speakers, Shahab Uddin, Yuki Kimura, and Amar Deep Tiwari instead of Jack Stelly, and Shub Luigi Jiang, and Urmin Begad. First, Shahab Uddin, could you please share your screen and start presentation?
Could you see my screen?
Our screen is not yet, okay. Yeah, you can start.
Okay. Welcome to my presentation. Today I will present the paper title is Quantifying the Relative Contribution of Climate Change and ENSO to Flood Occurrence in Bangladesh. This work is done when I was in Yamazaki lab. So the ENSO and flood relationship of Bangladesh is unclear by past research. Most of the finding was non-significant correlationship as well as conflicting relationship. Like this research find La Nina enhance the flood risks, whereas this research find La Nina decrease the flood risks. This finding can be inconsistent or conflicting because maybe due to three major reasons. First one is limited data because the ENSO character cycle vary 2 to 7 years, and second one may be due to use the observational data. This data is already contaminated by climate change, and then maybe the relative influence of ENSO become smaller. And third one, because of the second largest basins of the world, the GBM basin ENSO influence may be especially characteristics, and it is very river to rivers. So it can be better if you increase the sample data and then separate the climate impact from climate internal variability. For this purpose, here we use the D4 PDF large ensemble climate data consisting historical 100 members and non-warming 100 members. This data is generated by Part3 simulation suggesting slightly changing the initial boundary conditions. This boundary condition is generated by two perspectives. One is atmosphere chaotic noise is added to initial condition, and second one is sea surface temperatures. In case of historical data, sea surface temperature was observed, and in case of non-warming, it was determined. And then the noise corresponding to observation uncertainty is added to the baseline ST pattern. Therefore, the influence of climate internal variability related to SST like ENSO is involved in all experiments. So the D4 PDF can be suitable for climate change as well as ENSO-related weather hazard assessment. So the goals of this research to quantify the relative contribution of climate change and ENSO and flood occurrence. And methods for this purpose, first we simulate the river discharge using the CaMa-Flood global hydrologic models, and input was D4 PDF large ensemble climate data. And then we define the climate change and ENSO detection threshold. Here we use the 10-year return period. Then we estimate the flood occurrence probability for each phase of ENSO, La Nina and El Nina. And then we quantify the flood occurrence risk by ENSO phases La Nina and El Nina by comparing with long-term mean, indicating the normal condition of climate internal variability. And here we quantify the climate risk by comparing historical and non-warming flood occurrence risks. Here is the equation of the attribution framework. And now the result sections. No doubt, climate change significantly enhanced the flood occurrence across the river basin, Ganges and Brahmaputra rivers. But in case of climate internal ENSO risks, it shows the characteristic influence especially. Like in case of Ganges rivers, La Nina enhanced the flood occurrences across the river. But in case of Brahmaputra rivers, the major parts downstream is no influence of ENSO, where the precipitation is large. However, the amplitude of La Nina ENSO is almost equal to climate risks in Ganges and the confluence of these rivers, like 59% for Ganges and 64% for ENSO. However, here we also find the signal of ENSO is reduced in case of historical climate compared to non-warming climate. Like here is 0.38 far value, but here is 0.23 during the historical experiments. So the attribution of ENSO impact might be difficult in observed data due to contaminated by ENSO signal. So, and here we also assess why past studies found inconsistent results. When we consider the fewer number of ensemble, the correlation between the flood occurrence and ENSO is almost 80%. Bootstrap suggests non-significance. And we also find the quantitative result like positive correlation value suggesting El Nina enhance, and also negative correlation value suggesting La Nina enhance. And how many ensemble needed for attribution research? Here we suggest at least 30 member is better for attribution, for attribute ENSO impact on the flood occurrence. So now the summary and conclusion. The main point is D4 is suitable for climate change as well as ENSO influence of flood occurrence. And global warming obviously affect the interbasin, and La Nina enhance the flood occurrence in Ganges, and the changes flood occurrence due to ENSO are almost similar to the past global warming impact. So, large ensemble non-warming data is suitable for ENSO impact assessment because when we use the historical data, this data set is already affected by climate change, and then the relative contributions of ENSO may become smaller. So that is all from my side. Thanks for hearing.
Okay, thank you, Uddin. So yeah, this is a great research, and how to say, running large ensemble simulation is kind of something CaMa-Flood is good at. So I'm very happy to see this research. And the next talk is by Yuki Kita, and his talk is also about the D4 PDF usage. Kita-san, could you please share your screen and start presentation?
Okay, so can you see my screen?
Yes, please start.
Yes. Yep. So thank you for joining my presentations. This is my title, The Uncertainty of Internal Climate Variability in Probabilistic Flood Simulations using D4 PDF. So similar to the Uddin's research, I also use the D4 PDF large ensemble simulation. The background here is that creating flood hazard map needs a long-term hydrological simulations or observation data in broad areas. However, such a credible data is not usually obtained. Due to the lack of data, quantitative uncertainties associated with hydrological extreme values remain poorly understood. So if you see some flood hazard map, but it's based the difference on the the assumptions or the hypothesis. The global flood hazard map usually shows the different pictures. So the purpose of this study is to measure the uncertainty of a flood hazard map, especially the flood extent using the CaMa-Flood. So here is the methodology. So research question, as I said, is how large the uncertainties of flooded extent is in the flood hazard map. So using the CaMa-Flood and the D4 PDF Japanese one, 3,000 years, I implement extreme value analysis on river depths and flood extents and downscale into the 1 arcsecond and assess the uncertainty of the flood extent. So here is a calculation process that I used. So here's the results. First, I validate with observations. I look for the optimal place to measure the uncertainties. I found that here is Japan, Osaka areas, Yodogawa, the Takamo sites. I confirmed that the CaMa-Flood showed the good agreement with the discharge, observed the discharge. So I choose for the experiment site here, Yodogawa Basin. So here, I also validate with the public flood hazard map, the yielded flood hazard map by the CaMa-Flood 3,000 years simulations. So here, I don't do the quantitative analysis, but it seems a coincident. So sufficient length of hydrological simulation is needed for the extreme flood extent. So I will show it later. So here, the left one is the control RAM 3,000 years length simulations, and the right one is the uncertainty of the flood extent. So the black means that the fully coincidence in each ensemble members, and green and blue show the uncertainties. So using the single 60 years in ensemble, the river depths for a 1,000-year return period of flood scale have uncertainty between -11% and 9% in 3,000 years flood simulations. So it shows that's how different in the return period when the different climate variable simulation is used. The flood extent uncertainty with the return period 1,000 years was found to be the -8% to +7%. It means that the return period of simulation flood extent ranges from 300 years to 3,000 years. So it's a very huge uncertainties. So my conclusion is that especially at least for the 1,000-year return period flood hazard maps, at least the 3 times kind of the 3,000 years return simulation length is needed. So this study revealed that the conventional flood risk assessment may be overestimate flood extent and depth due to the internal climate variability. So longer simulation periods are essential to reduce uncertainty to improve flood hazard maps. So despite some modeling limitation, our findings enhance the reliability of flood risk assessment. So thank you for kind attention.
Okay, thank you very much, Kita-san. So this is also nice study using a D4 PDF and showing the variable of using a large ensemble dataset to address the uncertainties in risk assessment. Okay, so let me go to the next talk. It's by Yuki Kimura-san from MSAD. Okay, screen is shared, so if you are ready, please start your talk.
Okay, my name is Yuki Kimura, and my title is Methodology for Constructing a Flood Hazard Map for a Future Climate. Sorry, just a moment, please. Okay. This is today's contents. Contents is as follows. Firstly, background. In recent years, future flood hazard map have also have been utilized for corporate risk management, such as TCFD. This has created a demand for future flood hazard map. The construction of future hazard map relies on climate model predictions, so bias corrections is important. However, bias correction for future hazard map has not been well researched. And in this study, we examine methods for constructing future flood hazard map using CaMa-Flood. We compare two methods. One is lookup method, and the other method is simple bias correction. Simple bias correction corrects for bias in GCM runoff using the monthly climatology of reanalysis runoff. On the other hand, lookup. In next slide, I would like to explain the lookup method. Lookup method uses the GCM result without bias correction to calculate changes in the return period, and depends on the reanalysis simulation to determine absolute flood depths. At first, determine the return period, which you want to calculate in future climate. In this example, X. Nextly, determine the inundation depth for future flood for the return period X in GCM's future climate. And nextly, compare the current and the future climate of GCM to find the current year Z, which is equal to the water level in future X year. And finally, the water level in year Z of the reanalysis data model is used as the water level of future X years. In this study, we simulated global river and inundation dynamics using 3 types of runoff data. Firstly, reanalysis data. Secondly, GCM without bias correction. And lastly, GCM with a GCM runoff with bias correction. I created a hazard map. Left figure shows reference historical hazard map, and right figure shows a lookup method. Bottom shows simple bias corrections. And the right figure shows change from reanalysis data. Blue means increase, and red means decrease. Both two methods show the same direction in many rivers. However, in North Africa, the Mississippi River and the Amazon River area, the two methods show the opposite trend. And that's why we detailed study in Amazon River. The bottom figure shows the change from reanalyzed data in Amazon River. Left shows the simple bias correction. Right shows the lookup method. The bottom left shows that the simple bias correction decrease inundation compared to the historical data. On the other hand, bottom right shows the lookup method shows an increase in the compared to the analysis data. As shown in the previous slide, the two methods show opposite trend in flood risk changes for future climate. We checked the change in flood risk from present climate to future climate in CMIP6. Now we checked the change direction in the future climate in the Amazon River. The bottom figure shows flood risk increase in future climate in the Amazon River, suggesting that the simple bias correction may not be adequate for hazard mapping. And so lookup method could produce hazard maps that adequately represent changes in future climate flood risk better than simple bias corrections. Yeah, this is summary that we compared two methods in order to construct future flood hazard map. And in result, the lookup method is a good method compared to simple bias correction. Yeah, that's all.
Okay, thank you very much, Yuki. So yeah, it's very good to have a concrete method to construct future hazard map, even when the GCM output has a bias. And I'm also happy to have researchers from private companies joining this meeting. So thank you very much. So next talk is by Amar. Could you please share your screens and start presentation?
Okay. Do you see my screen?
Yes, but could you please switch to the presentation mode? Yeah, it's working now.
Okay. So good morning and good evening, everyone. I am Amar Tiwari. Today in this presentation, I'll be talking about application of CaMa-Flood model on reconstruction of long-term hydrological changes on island of Taiwan. And this is a published work in Journal of Hydrology Regional Studies, and this work was done by one undergraduate student at Michigan State University, and I had the opportunity to supervise this work. Yeah. So this work, as I mentioned, is done in a small island of Taiwan. So in Taiwan, typhoons are major source of water availability. 2 to 3 typhoons every year are very normal. And if there are more typhoons, there is flooding. And if there is less typhoons, there is a drought in Taiwan. So Taiwan faces an increasing risk of both severe floods and droughts due to its exposure to tropical cyclones. So in this study, we wanted to look into the questions which are, can large-scale hydrological hydrodynamic models accurately simulate stream flow and flood dynamics in Taiwan? And can such models reproduce hydrologic extremes such as floods during high-intensity typhoons? For that, we utilized HIGMAT runoff from 1979 to 2016 and CaMa-Flood model at 5 km to simulate river discharge, river depth, and flood depth. And then we further downscaled these flood depth to 90 meter. And then we evaluated and validated these simulations, river discharge, river depth, and flood depth with observations. Starting with stream flow comparison, here we selected nine stations in almost every major river basins here, and we found that the model simulates well even with the like coarse resolution of the runoff data, and also in a very small region. The model is like able to simulate the stream flow well. And apart from stream flow, model is also able to simulate water level, which is like river water level in these locations. However, there are some challenges. If you see, there is a high variability in observation data set, but in simulation data set, we see less variability in almost all stations. And in this study, we did not consider reservoir operations and also flood tunnel there is in the north. Next, we evaluated the flood dynamics simulated by CaMa-Flood, and we compared this data with GSW data sets at different locations, 2 locations in the north and here in 3 locations in the south side. And we found that model is able to capture these flood dynamics like very well in different locations in north and then south as well. Here in some locations, like if you see here, model is not able to capture very accurately. This might be the reason that this GSW data does not have like continuous period of record, and there's a lot of missing data. Next, we saw the trends and patterns of historical inundation in different decades, and here we see the changes from 1980s to 1990s, and we see minimal changes. In the north is like decreasing, and the south region is increasing. As if we move to closer decades, we see that the intensity has increased in terms of changes. Then we simulated these flood events on 2 typhoons, Typhoon Nari and Typhoon Morakot. Typhoon Nari happened in 2001, September 2001. And if you see here on 15th, 16th, 17th, and 18th, and on 19th, we see like the highest flooding, and then it starts receding. And then we compared the water level at different locations during this typhoon. Similarly, to Typhoon Nari, we also compared the flood, like we evaluated the flood at Morakot in different locations. And if you see from 8th, 9th, 10th August, and then it starts receding again. Also, we found that this like the model is able to capture the flood dynamics, water level during these extreme events of typhoon in Taiwan. So overall, to conclude, we saw that model is well simulating stream flow, water level, flood occurrence, and also decadal change in flood occurrence have increased over time that we found in this study. And not just the long-term mean, but also model is able to successfully simulate flood dynamics during these Typhoon Nari and Typhoon Morakot. Thank you.
Okay, thank you, Amar, for a nice talk. And yeah, we tried high resolution simulation in Japan, but we didn't try it outside of Japan. So this is a kind of a first case of using CaMa-Flood at a super high resolution, and I'm very excited to see this result. Yes, so please,
Thank you.
yeah, let's collaborate. Okay, so I'd like to move to the next talk, and the next one is a video recording by Shup Wu. So I'd like to start his video.
Today, I'm honored to present my research. The title of my talk is Climate Change and Urban Sprawl, Evaluating the Escalating Flood Risk in River Deltas with a deep dive into GBM River Delta. The first part is the background. Flooding is one of the most common and devastating climate-related disasters worldwide, and its frequency and impacts are intensifying. River deltas are characterized by low-lying terrain, dense population, and multiple economic and ecological functions, making them highly vulnerable to flooding. Global warming raises sea level rise, increasing coastal tides and storm surges. Climate change worsen extreme weather, increasing rainfall, storms, and flooding. As cities grow, natural landscape are replaced by impervious surface, leading to more runoff, high flood losses, increasing drainage pressure, and floodplain encroachment. Most studies focus on single-type flood indicators. Traditional assessments also look how expansion reshapes flood risk. To address this, we propose a high-resolution multi-source flood risk assessment to better identify vulnerable and improve disaster prevention strategies. The second part is the method. Our methodology consists three key steps. We use the PLUS module along with the hydrodynamic models like CaMa-Flood and list flood LP to predict urban growth and floodplain areas under different climate scenarios. The third part is the result. Our research shows urban area will expand significantly by 2015 and 2018, especially under SSP5. Pluvial floods have the largest impact, while coast floods affect the smallest area. Future projections show rising flood risk with coastal flooding increase the most. It's clear from those data that as urban expansion and climate change intensify, flood risk from coastal, fluvial, and pluvial flooding will significantly increase. A collective analysis showed that climate change mainly drives coastal flooding, while urban expansion significantly impacts fluvial and pluvial floods. Under the SSP5, both factors equally influence coastal flooding, but urban expansion plays a larger role in increasing urban flood risk for fluvial and pluvial floods. The final part is a conclusion. In summary, our finding highlights a key flood risk challenge: rapid urban expansion, especially under extreme scenarios, require proactive planning. Traditional assessment often misses the complex interaction of multi-flood sources indicators. Our scenario analysis shows that extreme climate change and urbanization lead to large flood affect areas in phases that need to robust mitigation. Climate change mainly drives coastal flooding, while urban expansion worsens fluvial and pluvial floods. Addressing those risks requires an integrated approach, combining climate adaptation with sustainable urban planning. That's all. Thank you for your attention. Thank you.
Oh, thank you very much, Shub. So I'd like to move to the next talk. And the next talk is also about video by Lu Jiang. So let me play his video.
Hello everyone, I'm Rui Zhejiang, and now I'm a PhD student from Tsinghua University. Thanks for Professor Yamazaki for giving me this opportunity to introduce my work here. I'm also very sorry I couldn't make it online. Today I will share my recent work about the flood risk of urban land in China. Floods are one of the most destructive natural disasters. China is greatly affected by floods. Over the past 30 years, the flood losses in China have accounted for about 10% of the global total. The flood risk is continuously increasing. One reason is that the water cycle is accelerating, leading to an increase in the frequency and intensity of extreme hydrologic events, such as floods. The other reason is that socio-economic development has led to increased flood exposure. Developing countries such as China are undergoing rapid urbanization. However, most of recent research have only considered increasing population and economic activity in existing urban areas, and the increase in urban land extent is not considered. Therefore, the flood risk of urban land may be underestimated. Based on the hydrodynamic model and the latest urban land projection data, we projected the flood risk of urban land under the background of climate change and urban land expansion. The foreseen data is from 5 base-corrected global climate model outputs, and 3 future scenarios were considered. The urban land we used is generated by machine learning and is the first 1 kilometer resolution map of future global urban land under the SSP framework. The hydrologic model we used is weak hydrologic model. The runoff generated by FIG is then used to drive the CaMa-Flood to generate the inundated areas. Only floods exceeding the 100-year return period are considered. This study focused on 7 major urban agglomerations in China. The land is classified as urban and non-urban land. Overall, the flood inundated areas in the Chinese region can be well simulated based on the FIG and CaMa-Flood model. In a changing climate, the frequency of the 100-year floods corresponding to the historic period is expected to increase across most regions in China, and this change is more notable in southern China. By overlaying the projected flood inundation areas with the urban land projection data, we found that the flood risk of urban land is projected to rise substantially in the future under the background of climate change and urban land expansion. What's more, there's a sharp rise after 2-degree warming. Considering the urban agglomerations individually, it's clear that the inundated urban land areas of the southern China will face the largest increases. We have also compared the flood risk of urban and non-urban land, and found that compared to non-urban land, urban land is more likely to be inundated. This is consistent with expectations and general knowledge, as most of the urban land is located along rivers. We have also compared the flood risk of original urban land and projected newly built urban land. The newly developed urban land will be more easily inundated than the original urban land in the Beijing-Tianjin-Hebei Central Plain, Central Shanxi Plain, and Triangle of Central China urban agglomeration. The opposite is true for the other 3 urban agglomerations. This is because that the different urban agglomerations have different expansion patterns. Newly built urban land in the Pearl River Delta and Chengdu-Chongqing urban agglomerations will be located away from the river, where others will be close to the river. This is the conclusions of our study, and the results demonstrate the urgency of integrating climate change mitigation, reasonable urban land expansion, and increased flood protection levels to minimize the flood losses in urban land. And that's all. Thank you for your attention.
Okay, thank you, Roger. It was nice talk, and yeah, obviously, how society change and how it changes flood risk is one hot topic recently, and those 2 talks are focusing on that. Okay, so I'd like to move the last talk in this session. Urmin, could you please share your screen and start your talk?
Hello everyone, I'm Urmin from IIT Gandhinagar. So I'll be presenting my paper on flood risk assessment for Indian subcontinental river basins. So in order to allocate fundings for the adequate flood mitigation, the government or the authorities need to develop the action plans, and they need to find the flood risk prone regions where it is needed to provide the adequate funding. So many global as well as regional studies are done, but if we talk about the India, so based on its complex geomorphology and the diverse climatic conditions, there is a need to perform this study on a finer scale. which covers the whole country. So the science question we address in this study are how the flood risk vary at the sub-basin scale during the long-term period, and which are the sub-basins where reservoir can play a considerable role in controlling the flood risk. So the data we have used is first climate data, which is precipitation and temperature from India Meteorological Department. And then we have used population data, which is from GHSL. And additionally, we have used global surface water data and a few observational flood data sets to find the flood events which has occurred in the history. So basically, we have calculated the flood risk based on the definition given by IPCC as a function of vulnerability, hazard, and exposure. So hazard and exposure is computed at our end, and the vulnerability is taken from a report which is made for India. So next, this is the model framework which we have used. So we have used runoff from the 808 model, and we have forced it into the CaMa-Flood model to get the stream flow and reservoir storage at different places. So here you can see the calibration and validation of stream flow at the gauge stations and reservoirs. So we have taken 50 major reservoirs of India based on their sizes, and they are calibrated on a daily scale for the reservoir storage. And additionally, we have checked the performance of a model for different flood events, with historical flood events with satellite from Sentinel, MODIS, and then the simulated results we have compared with that. So first talking about the influence of reservoirs on the flood extent. So we have used C ratio, which is the ratio of total upstream reservoir volume to the mean of the annual discharge at a selected point. So for that, we have taken the outlet of these sub-basins, and based on that, we have calculated the C ratio. So C ratio basically gives us the sub-basins where the influence of reservoir is high. So based on that, we can find the sub-basins where the influence of reservoir is high. So we multiplied it with the mean flooded area and maximum flooded area. So this will give us the basins where the flooding is higher, have been higher in the historical period, and the influence of reservoir is also higher. So in this sub-basins, the reservoirs can play a major role in controlling the floods. So then we have found the normalized vulnerability, hazard, and exposure for each of these sub-basins, and multiplication of these three gives us the risk. And again, we have normalized that value between 0 to 1. So here we are finding that the major risk persists in this area, which is the downstream area of Ganga River Basin and downstream of the Brahmaputra River Basin. So respecting the time, these are the few conclusions. So basically, we have identified the flood-prone sub-basins of India, and then we have identified the sub-basins which are most affected by floods in the history, and where the presence of reservoirs play a major role in controlling the floods. Thank you.
Okay, thank you very much, Urumin. I'm very happy to see the Japanese models, CaMa-Flood and HO8 are very appropriately used in India and has the usual very interesting result. So yeah, let's keep collaborating.
Yeah.
Okay, so let me move to the next section. So last session is session 2D, new data and tool for CaMa-Flood, and we have 3 talks. One is by myself, and another one is Menaka Rebel, and the third one by Yovjan Chen. So first, let me introduce about new tools in CaMa-Flood. So it's an allocate river gauge tool version 1.0. So allocation of river gauge on model river network. I mean the finding a model grid which is corresponding to the observation gauge location. That is very essential for enabling comparison of observed and simulated river discharge or water level. Well, in order to make a precise and appropriate comparison between the observation and simulation, this gauge allocation should be done in a very careful manner, considering potential errors in gauge attribute informations or river model's characteristics. So to achieve this purpose, last year we developed a new tool to efficiently allocate gauges on CaMa-Flood network and actually make it available as a allocate river gauge tool. So the description manual is here, and the package is available from CaMa-Flood webpage. So what is difficulty? So I'd like to say allocating gauges on a coarse resolution river map, such as CaMa-Flood map at larger than 10 km resolution. That is difficult because high resolution river network is not always precisely represented in a coarse resolution models. So let's focus on here. So if the gauges is in this point, it's easy to allocate. So the corresponding grid is here. But if gauges is in here, because of the tributary, this point doesn't correspond to the gauge, even though gauge is in this catchment. So we have to correspond it to the upstream. Or in extreme case, if the gauge is here, we cannot define the one corresponding coarse resolution model grid. And in this case, we have to think about a combination of several grid cells. So corresponding gauge location to a coarse resolution model grid, it cannot be directly done, only using latitude, longitude, or drainage area of the gauges. So this is a difficulty. So what this allocation tool do is we developed a 2-step allocation methodology. And step 1 is we allocate the river gauges onto a high resolution river network, Merit Hydro. And at the high resolution, actually, it's not so complicated to find the corresponding locations because most of the river channels are resolved. So it's not like a coarse resolution. We can easily find corresponding point. And what we do is, so this is kind of originally reported values of the latitude, longitude, and the drainage area. And by finding a corresponding location, we find merit hydro values of latitude, longitude, and the area. And because this value, merit hydro is used as a river network map of CaMa-Flood. So this value is consistent to CaMa-Flood map. So this is a point. So as long as we have a value, attribute corresponding to the merit hydro, it's very easy to allocate, find a correspondence between the gauge location and CaMa-Flood. So the allocation tool automatically correspond like this gauge location to here, and this gauge is to the upstream. Or in this case, we can say river discharge here should be compared to the summation of the upstream two grid cells. So allocate river gauge tool automatically do this process. So this is what we developed last year. But we have some issues, like many times the information of the longitude, latitude, or drainage area of the reported gauge value, it has an error. So what we actually do is a kind of a systematic error removal. For example, in this case, the gauge location was wrong, so we moved the gauges here. Or in this case, it's slightly off from the river channel, so we moved. Or in this case, it's on another river, so we check the name of the rivers or name of the reservoirs and modify. And but anyway, so this is unfortunate, but at least we did a quality check for GRDC gauges and the Grandi dam locations, and the error removed informations of these are also included in the package, so you can utilize that. So this is the end of the talk. So we've developed a new tools, and the allocate river gauge tool package is available on CaMa-Flood web page, and also we publish the code on GitHub. So if you are interested in, please use these tools, and I'm happy to further collaborate with you for allocating many information onto CaMa-Flood. Okay, thank you very much. And I'd like to move to next speakers. Menaka, could you please share screen and start your presentation?
Hope you can see my slides. So this is about Altimap. Altimap is basically for the same kind of allocation, but for the satellite altimetry data. So in satellite altimetry data, we have stations called virtual stations, where there is a river segment where it is crossed by a satellite track. Basically shown in these red yellow dots are the so-called virtual stations in a particular river, and these red lines are the satellite tracks. So I think from now you know that the CaMa-Flood course grid cells have can have an area variation among inside each grid cell. For example, in this figure C, we can see even though the natural slope is monotonous, but in the model we treated them as stepped wise elevations. So, but if the virtual station located in a middle of a grid cell, we need to somehow locate it to the where the simulations are corresponding to, which is the most downstream of that unit catchment. So we have developed a kind of a systematic way, an automated tool to relocate finding the most suitable location for each of the virtual stations published. For example, here we thought of like basically four kind of scenarios. Firstly, if we can find the virtual station original lat-long locations in the Merit Hydro River, we flag it as 10, and if it is in the land location near to the main river, we allocate it to the main river and flag it again. And also in the multi-streamed rivers, we try to allocate the location into the main river in that case. And in the coastal region, there are cases where we have to relocate those locations inward to the river as well. So such kind of flagging is important to see how the comparison of satellite altimetry data with the simulation is changing. And then also we have another treatment for largely where there is a large difference between the observed and the simulated values, because in some cases there can be some errors of the satellite altimetry data or the merit DM elevations. So we compare the mean value of the virtual station heights with the merit elevations, merit DM elevations, and included range where we can have the kind of best observations to use for the next step. So such kind of filtering is also included in this package. So in the data description, we report the particularly the some metadata for the virtual stations, and then we report the allocation results from the merit height related one, and then we convert them to the coarse resolution river network. So, for example, these IXIY and the datum conversion can be directly used in particularly the resolution of CaMa-Flood map you are using. And by this allocation, we found that most of the gauges were on the Merit Hydro River, but some of them have in the land, and we have to relocate them to the river. And very small portion of the gauges were found as the ocean pixels as well. So more importantly, by implementing this advanced mapping procedure, we could improve the root mean square and biases, reducing them by around like 10%. We could improve the comparison between the observations and simulation. On the other hand, we can get the distance from virtual stations to the river catchment mouth. From that, we can decide whether to use that virtual station for comparison or not. So this kind of advancement will be helpful in coming years when we compare the satellite altimetry data with CaMa-Flood simulations. Thank you.
Okay, thank you very much, Menakar. So this last result is very interesting. So this virtually shows that mapping the observation matters for evaluating the models. So thank you very much for your contribution. Okay, let's move to the last talk by Yojan. Yojan, can you share your screen and start your presentation?
So can you hear me, Sensei?
Yes.
Okay, I'm Yu Jiang in Yamazaki Census Lab, and today I'm going to give you a quick look at the dataset. I know most of you are the CaMa-Flood users, so when you do modeling the rivers, don't forget the reservoirs, and the reservoirs can regulate rivers by control affecting its timing and water amount to release downstream. So when we are developing models, on the other side, we have to take more concern about the dataset aspect. So in this sense, I developed the satellite-based reservoir dataset. This is not limited to the CaMa-Flood users, but can also be support a wide range of interesting users. So this is a graph, and we can see the reservoirs impounded water behind it. So it's not only collects the waters from the upstream, but also collects the materials from the upstream. So currently the research gap is that most of the previous studies focus on the develop the certain type of the variables, such as the water level or water area from the Landsat. But the second part is that no data set exists for the reservoir catchment level characteristics. So, and our contribution is to integrating all these data sets and to provide a very comprehensive data set in China. And you can find the data sets through this data link. And the first message is that we enhanced the satellite-based reservoir states through multiple satellite altimeters such as laser and radar altimeters, and processed the images from not only the Landsat but also the Sentinel satellites. So we enhanced the spatial and temporal resolutions for Chinese reservoirs. So this is a glimpse at the water level, and we matched the multi-source satellite datasets. And our projects provided two projects for the water level. The first one is a standard rate. That means the water level time series is only contained from the certain type of the satellite. And another rate is a high rate water level product by merging the multi-source if they are available. And here is some figures to show the water areas and water storage variations for the reservoirs. And we conducted the detailed validation using the satellite, other projects, and also using in-site water level datasets. And the second part is that we provide very comprehensive reservoir catchment attributes. And this is two types of the four reservoir upstream catchments for and we so-called the full catchment, and but for this some have some problem with, and we may lose some local vulnerabilities if the reservoir is quite large. So we provide the second type, that's we call the intermediate catchment. And using these two types of the catchments, we extract the over 500 attributes in 6 categories. And then what insights does the reservoir in China can offer? So I give you like 3 tips here. The first one is that we can use the upstream reservoirs to using the catchments. We provide such links so we can check the water quality and flows through this data set. And the second one is that we can provide the reservoir state, so we can use it for water resource management, and you can do predictions predict the water storage changes 1 or 3 months ahead. And third one that many studies found that these upstream catchments affect the water quantity, water quality, and CO2 emissions. So you can use these to do something. And that's all for today's talk. So thank you.
Okay, thank you very much, Georgian. So yeah, preparing data set is very important to advanced CaMa-Flood modeling and simulations. Okay, so thank you very much. And I'd like to make some last announcement. So yeah, thank you very much, everybody, for making a very exciting presentations. And I'd like to make some additional report on community activity. So yeah, some of you joined, but we had our CaMa-Flood user developer meeting in July 2024 in IISU Tokyo. And the meeting note is available here. So yeah, today's one is kind of not interactive because of the time limitations, but yeah, we how say but this user developer meeting is more interactive face-to-face discussions. And last year we had 83 participants gathered in Tokyo, including 34 people from 11 countries overseas and 49 from within Japan. And we had 23 oral presentations and 15 posters divided into 8 sessions. So I think we had a very good discussion. So thank you very much for participating in this event. So, actually, this interactive face-to-face discussion was very helpful. We are thinking about the next opportunity. So the next CaMa-Flood developer user meeting, we are planning to have the second one, possibly in September 2026, next year in UK. And now we are adjusting the details. And so, yeah, I will share the information as soon as the detail is fixed. So please wait for the decisions. But yeah, let me repeat. It will be in September 2026 in UK. So I think many people in Europe can easily join. And so this is about the meetings. And also from this year, we start organizing session in AOGS, Asia Oceania Geoscience Society. So we have our sessions named Advances in Large-Scale River Modeling, Development and Applications. And myself and Peyron Lin, Fitzmoon Oldemeskel, and Shudon Zhou being conveners. And this year we invite Dr. Ki-Hon Tans and Dr. Gray Needing from CAS and Google as our invited speakers. So unfortunately, the abstract submission was already over, but if you are joining AOGS in Singapore, please join our sessions. So this is our community activities. Anyways, thank you very much for joining this annual briefing. So this is a very fast attempt for us, but I think it worked very well. And I'm happy to see many reports on your published works. So this year was successful. So I wish, or I have said, let's make the year 2025 productive again, and let's gather next year. Thank you very much.